Have you ever just stopped and wondered how AI got so good so fast? I mean, from writing code to making art, the leap has been incredible. Well, it all comes down to one brilliant idea, a single architecture that's the engine behind this entire revolution, the transformer. So let's pull back the curtain and see how this one big idea from 2017 is literally shaping our world. But, to really get why the transformer is such a big deal, we have to look at what came before it. What was the massive problem that AI just couldn't crack? Well, it all boiled down to something very human, a terrible memory. The core issue was what everyone in the field just called the memory problem. Before the transformer came along, language models had this fundamental flaw in how they processed information. It made it almost impossible for them to remember the context of what they were reading, even across a few sentences, let alone a whole document. So, the main players back then were these things called recurrent neural networks, or RNNs for short, and they were built to handle sequences, like text. The idea was pretty simple. Read one word, update your internal memory, read the next word, update again, and so on. Sounds logical, right? But yeah, that step-by-step thing, that was the big, fatal flaw. Here's the best way to think about it. An RNN reads a sentence like you might read it out loud. One word at a time. By the time it gets to the end of a long paragraph, its memory of the beginning is all fuzzy and weak. But transformers? Whoa! They just look at the whole page at once. All of it, instantly. So how do you go from that slow, forgetful model to one that can see everything at once? It feels like a massive leap, right? And it was. The entire AI world changed because of one single paper that dropped in 2017 from a team at Google. And the title was just brilliant. Attention is all you need. A great nod to the Beatles, for sure. But this wasn't just some small tweak. It was a total teardown and rebuild of how we thought machines could understand language. The title wasn't just a catchy phrase. It was a bold statement that a new era had begun. Now, this didn't just come out of nowhere. The core idea, attention, had been kicking around for a few years, but it was basically just a little helper, a bandage for those old, slow RNNs. But what the 2017 paper did was radical. They said, forget the old model, let's get rid of it. They threw out the entire sequential engine and built something only on attention. And it more than worked. It kicked off the AI explosion we're living in right now. And the human story behind this is just, wow. It was written by this team of 8 researchers at Google, and they were so committed to the idea that everyone contributed equally, they actually randomized the author order on the paper. But here's the kicker. After dropping this bombshell, all 8 of them left Google. They went on to found their own companies or join other big AI labs, basically becoming the apostles of the transformer, spreading the idea everywhere. Okay, so we know transformers can see the whole picture at once. But how on earth do they make sense of that jumble of words? Let's break down how this thing actually works under the hood. The magic ingredient is something called self-attention. Think about it. When you read a sentence, your brain is subconsciously linking words together. You know who he refers to or what it is. Self-attention is the AI's way of doing just that. For every single word, it looks at all the other words in the text and asks, how important are you to my meaning? It builds this incredible, complex web of connections all at once. Okay, but wait a second. If it sees all the words at once, isn't word order important? I mean, dog bites man is not the same as man bites dog, right? Exactly. That's where a really clever trick called positional encoding comes into play. It's like adding a little invisible number or a timestamp to each word so the model knows this was first, this was second, this was third. It preserves the order, even when looking at everything simultaneously. So let's walk through the whole workflow, high level. Step 1, the text gets chopped up into pieces or tokens and turned into numbers. That's called embedding. Step 2, we add those positional signals we just talked about. Step 3, self-attention goes to work, creating that rich map of context. And finally, step 4, with all that deep understanding, the model makes its best guess for what word comes next. That's it. So the original transformer was a masterpiece. But of course, the story doesn't end there. The community took this brilliant idea and immediately started refining it. And a huge step forward came from Meta with their llama models, which really proved a new philosophy. It's not just about being bigger, it's about being smarter. And their genius was really in the details. They didn't try to build a whole new car from scratch. They took the incredible transformer engine and just upgraded the parts. They swapped in a more efficient normalization method, a better activation function for more nuance, and a more sophisticated way to handle word order. Each one was a small, smart upgrade that added up to a huge performance boost. This whole philosophy was a total game changer. For a while, the race was all about who could build the biggest, most massive model. Llama said, hold on, what if we build a smaller, more efficient model, but we train it for way longer on really, really good data? And wow, did it work? Their model was a fraction of the size of giants like GPT-3, but it performed just as well. That's the definition of smarter, not bigger. Okay, so the architecture is brilliant, and now we've made it way more efficient. But there's still a bottleneck, right? All those self-attention calculations are incredibly demanding. The next huge leap wasn't about changing the architecture, but about making it run screamingly fast on the hardware we all have today, our GPUs. And that's where this incredible algorithm called flash attention comes in. Just look at this chart. It shows how much of a GPU's power is actually being used. The older version was leaving more than half the horsepower on the table. But the new version, Flash Attention 3, it's using 75% of the GPU's potential. This isn't a new chip. This is just smarter software letting the hardware really stretch its legs. And what does that speed look like in numbers? Well, we're talking about 740 times trillion calculations per second. That number is just mind-boggling. It's this kind of insane speed that takes processing huge documents from a theoretical idea to a practical, everyday reality. All right, let's connect all the dots. We solved the memory problem with parallel processing. We made the architecture way more efficient with smarter components. And we made it run incredibly fast with better software. So what? What does this all mean for you and me? It all adds up to one thing, the long context revolution. Just look at this timeline. The progress is absolutely staggering. A few years back, an AI could maybe read a few pages of a document at most. Then it jumped to handling a short story, and now, thanks to all these innovations working together, we have models that can process 1 million tokens. We're talking about feeding it an entire novel, like The Great Gatsby, in one shot. And this isn't just about showing off a big number. It fundamentally changes everything. It means you can ask an AI to summarize a whole book. You can have it analyze a dense financial report, or debug thousands of lines of code. You can have a conversation that lasts for hours, and it will remember what you said at the very beginning. That old memory problem, it's not just solved, it's ancient history. So when you look back, the journey has been absolutely incredible. From these old, forgetful models to today's million-token powerhouses, we've conquered the foundational problems of memory and speed through just brilliant architecture and relentless clever engineering. Which, of course, leaves us with the big question. Now that we've solved these problems, what's next? What is the next great frontier for AI?